Now I don't. So good morning, everyone. Thank you for being here so early. 10 is early on the second day of the workshop. So I hope you had a good time yesterday. You're all well rested. So we'll continue from where we left in the morning session yesterday. The afternoon was a little bit different. So let me remind you, we were discussing something like this, that if you take a single degree of freedom system, then if you allow it to vibrate under the influence of fluid force from springs, then you get a region of desynchronization where you have very low amplitude oscillation. And then you get a region of high amplitude oscillations. I should put my camera. No. Okay. Can we minimize this one? Thank you. Thank you. Possible to break it on? Okay, no? Very nice. No, it's okay. Actually, we can, if it doesn't shoot the at the bottom, I think it will go, that's fine. Menu is, I think this is perfect. Okay, great. So, there are a few questions that remain unanswered. For example, I talked a little bit about it yesterday. Why is this the range of lock-in? Okay, why does the lock-in begin here? Why does it end here? How does the system know, the fluid structure system know that what should be the frequency of vibration? And how does it decide on the amplitude? Why is the amplitude large here? Why is it relatively small? So those questions remain. We don't have an answer. Just to remind you, during lock-in, essentially the frequency of vibration goes very close to the natural frequency. But it is not exactly the same as in resonance. Depending on the mass ratio, and I gave you some examples, it could be a little bit off. So that's another thing. Who decides the frequency? So if it's the natural frequency, it's still understandable. But if it is something in between, either the vortex shedding frequency for the stationary cylinder, neither it is the natural frequency, and somewhere in between. So who decides that? Those are some very pertinent questions. Okay, where are they coming from? So to do that, let me give you a brief account of this block body, the flow past the cylinder. So we have to understand where are all these instabilities coming from, who is getting excited, what is the spring doing, and so on. So broadly speaking, if you look at flow past the cylinder, as I have shown in this cartoon, this was done very well by Professor Williamson. He says that there are three possible instabilities. The first one is the wake instability. So if you look at the flow past the cylinder, there's a wake here, that velocity profile has a recirculation zone. It turns out beyond a certain Reynolds number, if you disturb that, it becomes unstable. Okay, so vortex shedding will begin. And that's because of the instability of the wake. Then there is this shear layer. Okay. So the shear layer itself could also be unstable. So there is so the flow separates, and then the shear layer goes up into small vortices because of an instability. And it turns out at low Reynolds number, when the shear layer is unstable, the instability will be a little bit downstream of the cylinder. And then as you increase the Reynolds number, they move upstream. That's the shear layer instability, which is very different than wake instability. And they will have different frequencies, they will have a different structure. In fact, they're quite different qualitatively. I'll say that in a minute when I go to the next set of description. The third instability is that of the boundary layer. So the boundary layer, which is laminar, for a range of Reynolds number. So I gave you some examples of Reynolds number 1000 yesterday. So the wake is unstable at Reynolds number 1000. And in fact, there could be some turbulence also in the wake because of the instability saturating. But the boundary layer is completely laminar. If you go to a Reynolds number in the critical range, it could be of the order of maybe 2 into 10 to the fifth or 3 into 10 to the fifth, then the boundary layer can also become unstable. And it will then transition to a turbulent state. So essentially, we are talking about three instabilities. The wake instability, the shear layer instability, the boundary layer instability. And now you add a spring to it. The spring has its own modes, unstable modes. So if I'm a structural mechanicist and I ask myself what are the modes, let's say a cantilever beam, you can talk about the first natural mode, second natural mode, third natural mode. So in that sense, if this is a tall building, the building will have its own mode shapes. So those are additional instability. And now all these could interact. So the bottom line is, the higher the Reynolds number, the more complicated is the situation. So we restrict ourselves to very low Reynolds number. Okay, mostly in the laminar regime, where you don't have to worry about shear layer, you don't have to worry about the boundary layer instability, just the wake instability. But as you keep going to higher Reynolds number, you really will have to worry about it. Okay, just to give you a primer, the flow past the cylinder is itself very, very interesting. So at very low Reynolds number, you get a Stokes flow, there is no separation. And then as you increase the Reynolds number, these two tiny vortices appear in the wake. And they grow in size as you increase the Reynolds number. So this is a very nice visualization. It was actually done through by putting in creamer in the wake. So the visualization was, condensable. So you put that and you can visualize the vortices. You can notice there's some stuff going on here. So there's already a little bit of unsteadiness. So the flow everywhere is steady, it's not changing with time, but there's a small unsteadiness here. So it already gives you a hint that probably something is happening here. And then as you increase the Reynolds number, you get this beautiful vortex street, which all of us know, the Karman vortex street. So just to describe this vortex street, the incoming flow is steady. So imagine the input is steady, the cylinder itself is steady, but the output is unsteady. So one could ask, who is causing this? And clearly that's self-excited. Nobody has to do anything. So the steady flow past a circular cylinder at this Reynolds number would be unstable. So if you perturb it a little bit, then these instabilities will grow. So the question is, can we try to understand them? Can we do something to find out what these instabilities are, how they grow, why they don't grow or lower Reynolds number, why they grow for number. And you get these for other bodies also. So you cannot say that only because the body is very bluff, you will get vortex shading instability. Even for thin ellipse, I have shown you can have a weak vortex street. So it is there. So it's really a property of the wake. Then of course you saw these pictures yesterday in the second half, where the boundary layer would become unstable through some boundary layer instability, and you get a transition from a laminar boundary layer to a turbulent boundary, and then it has its own implications. But we are not going to worry about that today. Okay, so as an analyst, what kind of tools could one have access to essentially look at these flows? So you could do a full DNS, okay, a direct numerical simulation. So DNS at low Reynolds number is fairly simple. Just have to resolve all the scales. But as you keep increasing the Reynolds number, then things become complicated. So DNS would be more challenging. But we will restrict ourselves to low errors. In fact, laminar flows the rest of the problem. You could also do DNS by coupling it with a structure. Okay, so Professor Bose yesterday talked about the coupling. So you could have a monolithic coupling and you intricately couple the fluids and structures. You could also have a loose coupling, and then there are pros and cons. But you could, in principle, do a tightly coupled system, or you could set up something to do a loosely coupled. You could also do a DNS, direct numerical simulation, not just with the real equation, but just the disturbance equations. So you can subtract the steady flow and write down the disturbance field. And so actually these two problems are same. It's just that the way of looking at it is different. The advantage is that you could do either a full nonlinear, or you could say I will drop the nonlinear term and try to understand that when the disturbances are small and I can neglect the nonlinear term, then what is the system doing? So essentially the way the system behaves, is it because of nonlinearity, or it is some intrinsic linear problem which is manifesting in the field? You could also do a stability analysis. So you could take these disturbance equations, the linearized disturbance equation, and put in some known eigenmode and try to do some analysis, and then talk about whether your steady state system is stable or unstable. And I will talk about that in the coming slides. So we have this concept of global instability and local instability. Are you aware of global and local instabilities? Maybe I will just say something. So you are aware of the Orr-Sommerfeld type of analysis? Maybe some of you. So if I look at flow on a flat plate, okay, the Blasius boundary layer, okay, it is a self-similar solution, right? Or rather, it's a similar solution. So there's a Blasius profile at all streamwise locations. Just the scaling is different because the boundary layer thickness will grow. So I could do a local analysis. So I could take a profile at any station and say, well, if I do analysis of this profile, I know everything. And that's not true, because effectively the Reynolds number based on X, the streamwise location, is also changing. Okay. Then you could say, well, I will just keep Reynolds number as a parameter, but it's just the Blasius profile, and I will just look at a local analysis, which is the Orr-Sommerfeld analysis. So that's an approximation, but it works well in many situations. The more general modeling approach would be you take the full three-dimensional flow, okay, calculate the steady state, and then perturb it and do a stability analysis of that. And that would be a global analysis, because now you have a global eigenmode versus a local eigenmode. Then there is this idea of a convective versus absolute instability. So I will show some slides to push that idea, and I'll tell you why it is important. You can also do stability analysis of a time average flow. So suppose I have done a DNS and I already have a limit cycle. Now I average it, and maybe if I do a stability analysis of that flow, it will reveal something. So I can try my hand in. I could do a linear stability analysis of the fluid structure problem. So I do the full stability analysis, and maybe that's what we should do for this system. Okay, we take the fluid equation, we take the structure equations, the coupled ones, and then we do a stability analysis. And maybe that will tell us the coupled frequency, the coupled eigenmodes. Right, I will show you that. Okay. And then you can talk about the sensitivity, so I will not say too much about it. You could also do proper orthogonal decomposition. Are you aware of this term? Some of you maybe. So the idea is very simple. Suppose I have a flow. So maybe I'm doing an experiment. Okay? And I can make a movie of flow. And I can choose maybe a few snapshots, 100, 1050, whatever I feel like. And I can ask myself that in these 50 or 100 snapshots, what is it that is the most important feature? Okay, so now I can construct a basis based on what are the important flow features. So there's an animation going on in which I have this vortex shading, and I can ask myself, in all these 100 snapshots that I have, what is the flow feature that is occurring the most? Okay? And which is the one which is the second frequent, the third frequent, the fourth frequent, and I can list them. Okay? So that way I can also form some eigenbases or eigenmodes of that, and I will show you some examples. That's also very useful. Okay, so let me say a little bit about linear stability analysis, because I will show you some linear stability analysis. So I want you to get familiar with this. It's a little bit tricky for those of you, if it's the first time, there will be a lot of things that you may not understand. It's okay. Hopefully you'll get a general idea. So as I said, there are two possible approaches, a local and a global. In the local approach, you will look at a local flow profile. So suppose I am interested in flow past a cylinder or an airplane, then I can just take a velocity profile at a certain location and do a stability analysis of that. Okay. It is in the same sense if I want to understand the stability of this group of people. Okay. In the sense that suppose somebody throws a stone here, what is the reaction of this group? Okay, does it explode? I mean, does this community explode? Or does it become calm after a while? So it's possible that if there's a small disturbance, people will just leave the room, it will just explode. It is also possible that there's a small disturbance, people will say a few things, but they will say, okay, this is a small event, and get on with their lives. If I want to analyze the group, I can do it two ways. I can analyze you person by person, individual by individual, and say, okay, if I understand a few individuals, maybe it is representative of the whole thing, and I can get some answers. But probably a better way is to do the analysis of the whole group. So you can think of some such thing going on. So you can use simple equations, or our field is a much simpler equation. And you repeat the analysis for different stations. The global is you make the entire flow, you make no assumption, and of course this analysis is going to be expensive. Okay, so I'm going to show you today global analysis because that is more relevant here. Local analysis doesn't give us much, okay, for fluid structure. Okay, so the other idea is the convective versus absolute. Okay, so if you understand it, fine. If you don't, you will not lose much. Okay, I'll give it a try. So the idea is very nice. So if I put a disturbance, so imagine, so I think the best example I can give you is of a fire. So imagine there's a big forest, okay, and there's a fire at some point, and this fire is spreading. Obviously, a fire will spread. So there's a point of location, and it's spreading. That is one way of thinking that this fire is unstable and it is spreading. Suppose there's a very strong wind. Okay. Then this fire actually goes in one direction. So it spreads, but it spreads in a certain direction. Now the two situations are very different. In one case, it's kind of isotropic, it's going everywhere. And in another case, the instability is growing as it moves. Okay, so there's a convection involved with it. And that's why this is absolute versus convective. So an absolute instability is something where the disturbance grows at the point of generation. And the convective is where it can travel as it grows. Okay? So this is very important from an observer point of view. So again, coming back to a forest fire, if I keep a station and say that I will find out whether there are unstable fires, and I put two stations, let's say in the entire forest, okay, that may not be enough. But if I have in mind that these fires could also grow while the origin is changing, then I can have a better, maybe I can have an air station which is global or whatever. And obviously the classification will depend on the frame of reference. So, so if there's a moving instability, I can actually move with it, and that observer will say, hey, I see this as an absolute instability. It is not convective. So that ambiguity is there. So these are some diagrams that will help you. So this is the origin. That's the x-axis. That's time. So imagine a disturbance grows somewhere. It's ended somewhere, but it decays while it is moving. So notice the x location is changing, and with time, the amplitude of this disturbance is decaying. So this is a disturbance that decays with time, so it is stable. Okay. In a convective sense and in an absolute sense. Look at this one, the B. Okay, this one is growing, but it is moving as it grows, especially at the origin, at the x location where it was originating. There it is decaying with time. Okay, so this is actually a convectively unstable disturbance. You look at this one, or you look at this one. This one is a border case. This one is actually it is convecting, but it is definitely growing at the origin as well. So this is an absolute unstable. Absolute instabilities are very strong. Convective instabilities are not so strong. They will be washed out eventually. But absolute instabilities keep on giving feedback, and they are very, very strong. Okay, so they are also called self-excited. So imagine I had flow past a circular cylinder, and if I had an instability that grows, but it also travels, then eventually it will be washed out. I have nothing to worry about. Maybe another packet will come, it will be washed out. But if I had an instability that grows where it originates, then it is there to stay. Then you can see it will excite the flow, and my flow will be, it will go through a limit cycle eventually. So some backgrounds have been described here. So as we said, this is linearly stable, this is linearly convectively unstable, and this is absolutely unstable, and marginal problems. Okay, so I hope very quickly I've given you two concepts. So first we talked about an instability, then absolute versus convective, and local versus global. Okay. The entry of the boss. Huh? We were just talking about an instability and a disturbance. No pun intended. So these are, so Subhankar, this was the last slide just to give the perspective. Okay, so the incompressible flow equations, so there's the moment, the mass balance, the continuity, and then the momentum equation, and of course the Newtonian fluid and so on. What we can do is we can derive a disturbance equation out of it. We can split this U and P, the velocity and pressure, into two parts. A steady state part and a disturbance on top of it. And same thing, a steady state pressure and a disturbance on top of the steady state. So that's what is given here. U and P are the steady state, uppercase, and lowercase with prime are the disturbance field. What I can do is I can take this decomposition and put it in these equations. So I can write this small u as capital U plus U prime. Same thing here. And the sigma has a P inside it, and of course the Laplacian term. So I can just expand it. So I'm not doing all the arithmetic. It takes a little bit of time. But you should do it because it will give you confidence. You will get two terms out of every term. Okay, one based on the steady and one based on the disturbance. But the nonlinear term, this guy, will give you four terms. because this will be capital U plus U prime, this is capital U plus U prime, and then when you expand it, there will be four terms. One of them will be capital U dot gradient of capital U, that's the steady state one, and the others will involve U prime. So that's what is written here. So what I've done is I have subtracted the capital U and capital P terms from the equation. Remember, the steady state equations are satisfied by the steady state solution. So if I take capital U and capital P, then they actually satisfy these equations without the unsteady terms. So divergence of capital U is zero because it's a steady state solution. Similarly, capital U dot gradient of capital U minus F, divergence of capital sigma is zero. So what I've done is I put this in the equation, subtracted the steady state, and then I can get an equation just for the disturbance. So from the convection term, I have four terms. The steady state term is gone, and I have these three terms remaining. Notice these two are linear terms because they involve U prime only once. This guy involves quadratic form of U prime. So this is non-linear. So now I can make assumptions. I can say that I am interested in looking at disturbances that are very small. So U prime is very small, and this term would be of the order of U prime square, so it's even smaller, and therefore it doesn't contribute much when the disturbances are small, and I can get rid of it. When U prime becomes large, then of course I don't have that luxury, then I have. And same thing with the current. Okay, now I assume a very special kind of a disturbance. Okay, so I will assume this disturbance. The disturbance is U prime has a spatial part, the eigenmode, and in time it behaves like e to the lambda t. These are standard eigenmodes that everybody assumes. And same thing for pressure. The only thing is that these two parts, the spatial parts, they can actually move in space to look at convective instability. So C is the speed of the disturbance. If I put it equal to 0, then I'm only tracking the absolute instability. If I put C as non-zero, then I can also track convective instability. In this analysis, we will be mostly doing C equal to 0, so you don't have to worry much about the non-zeros. Okay, so I can substitute that form and I get an equation like this. And now this becomes an eigenvalue, eigenvector problem. Of course, it has these derivatives which I'll have to worry about, but eventually it becomes an eigenvalue, eigenvector problem. So it's just like your Ax equal to lambda x kind of a problem, a little bit more complicated. So I can track the eigenvalues, I can track the eigenvectors, and maybe get some physics out of it. For those of you, if this is the first time exposure, you will find it a little bit tricky, but you can read any book and you should be able to follow. Just to go step by step. In general, the eigenvalue is complex. Okay, so it has a real part, it has an imaginary part, and we can show that if lambda is an eigenvalue, its complex conjugate is also an eigenvalue. So in other words, if I'm doing a linear stability analysis of any flow problem, the following can happen. I can have completely real eigenvalues, or I can have complex eigenvalues, and these eigenvalues will appear in conjugate pairs. And they have a certain meaning. So if I go back to e to the lambda t, if I put lambda as lambda real plus I lambda imaginary, then the lambda real part just gives me exponential growth. So if lambda r is positive, that means my disturbance will grow with time. If lambda r is negative, it decays with time. Okay, so if I solve this eigenvalue problem, I will be able to see whether a disturbance will grow or it will decay in time. The imaginary part As you know, it will be lambda RT, so that has sine and cosine components. So that means it is fluctuating in time. Okay. So that will give me some idea about the vortex schedule or the frequency associated with that eigenmode. So I can get both the information, something about the Stokes number, the vortex shedding frequency, and whether the disturbance will grow or decay. So again, lambda r is the growth rate, and lambda I will tell you the temporal frequency of the disturbance. Okay, I can skip this slide. We will do it mostly for C equal to 0. So we can write down a finite element formulation for the base equations. We can write it down for the disturbance equations and solve it. Not very trivial, but it can be done if you are careful. Okay. So let me show you what we were able to find out. When does the flow become unstable? It turns out that even at Reynolds number 4, you could have a convective instability in the flow. Remember, I showed you one picture where there was a stable bubble, but there were some disturbances towards the end of the recirculation bubble. So, our calculations show that even at 4, you could get an instability. Actually, this work was done by Professor Sen. Very landmark work. It was not known when does the flow actually separate. The first time separation of flow on a circular cylinder. A lot of contradictory numbers in the literature. So Professor Sen carried out very careful calculations. And in fact, that work is very well cited. I hope you have been following that. Everybody cites it. Anybody who works on circular cylinder. And the first big instability, which is of course an absolute instability, so it's self-sustained, happens at Reynolds number 47, and that leads to one carbon shedding. So all this has come from stability analysis, which I showed you. Then there's the shear layer instability, which I alluded to in that cartoon from Professor Williamson. I mean, there is enormous contradiction in the literature. So in 64, June said it appeared at 1300. Then Gerard said it appeared at 350. It is a lot of scatter. So using our method, we were able to show actually it happened at 54. Okay. So it's very interesting. 47, the wave becomes unstable and the shear layer becomes unstable at 54. So there's something going on. This is not very important for us. This is. Okay, so we focus on that. So just for completeness, I included a slide from Professor Sen's work. So I was very happy when he walked in. Actually, this picture was made by Professor Sen. I hope you remember that. A very interesting time. He kept making pictures and I kept suggesting modifications. It was very kind. So these are points of separation and points of the reattachment. So the question that Professor Sen was asking is, what is the exact Reynolds number onset of separation, and where does the separation begin? Because some people were saying, you know, the flow could separate all of a sudden at some location, but the hunch was it should separate here, okay, at the base point. So he did a lot of careful calculations. So there you see the God himself. Yes. So he was able to show that actually the flow separates, and then with Reynolds number he was able to carry. In fact, he showed that people are finding so much scatter in the literature because it is very sensitive to the boundary conditions. So he used different kinds of boundary conditions, flowing time, slip boundary conditions, and he was able to show that if you plot with blockage, blockage is essentially if I take a body. So suppose this is my wind tunnel, the flow is coming towards you. So I put a cylinder end to end. and I take a cross section. What cross section of this wind tunnel, that percentage is occupied by the body? If that percentage is very large, obviously the flow will be altered by the walls. Okay, because it can't go away from the body. So it will be very constrained. So he showed that if you have a blockage of large blockage, then it is very sensitive, but if you have low blockage, then of course it reaches this asymptotic value. He was able to show how others making these erroneous results. Okay, so we now come to the first instability. So mind you, we are still doing an isolated cylinder, and soon after this, I will be showing you fluid structure system, but a similar analysis. So I'm warning you all. Are you able to follow more or less what I'm saying? Details will not be clear to you. I'm very aware of that. But at least are you able to get a general feeling of what is going on? Okay? Yeah, please. So we will look at now the first instability. So this is what the answer came out. So this is the growth rate, and this is the C, and this is for different Reynolds number. Okay. I will skip this. I will just show you the eigen modes. So this is the steady flow, and this is how the eigen modes would look like, the real part and the imaginary part. The cylinder is there. So that's the Reynolds 4. We are not interested in this instability, we are interested in the absolute instability. So I will skip this. So that's what it is. So if you look at Reynolds number 50, okay, and you want to look at the instability of the wave, then this is how the mode looks like. Okay, so this is the disturbance field, okay, that is responsible for potentially. And if you do a direct numerical simulation, so you take the Reynolds number 50 flow and put a small disturbance. Actually, it looks like this. So it looks very similar to what the eigenvalue analysis gives you. Magic. So there is a lot of scatter in the literature as to what is the commencement of vortex shedding. So some researchers, their results are listed here. For example, Kowalski said the flow becomes unstable at Reynolds number 40. Even you can see with increasing experimental technology, the number has refined. And this is what was found by our group, 47. But there is a very large scatter, all the way from 40 to 50. Because which is the correct number? Again, we found it is very closely related to the blockage. So some calculations were done. So this is the domain size, this is the critical Reynolds number, this is Stuart number, and we drew a curve. And it turns out everybody's data actually, based on their domain size, actually lies on this curve. So we were able to show that the critical Reynolds number would be by extrapolating the domain size to infinity. Okay. Now the real thing begins. Okay, this is the background. So let us consider Reynolds number 100 flow past the cylinder. This is your steady flow. I want to do a stability analysis of this particular flow. This is the vorticity field. So I do the disturbance equations. I set up the eigenvalue, eigenvector problem, and I hunt for the eigenvalue which has the largest real part, because that will be most unstable. So these are the two parts that I get, the real and imaginary. So the first unstable eigenmode would be real plus I of this positive value. The conjugate part would be real minus I of this imaginary value. Okay. You can see these two modes are essentially same. It is staggered. Okay, if you look at these flow structures, okay, they look very similar, but they are a little bit out of phase. This blue is shifted a little bit to the right. This red is shifted a little bit to the right. Otherwise, they look very similar. This is the Struve number that comes out of the instability, the imaginary part of the eigenvalue. Okay. Now, those of you who remember the vortex shedding frequency at result number 100 would realize it is actually much larger than this. So, what is going on? So, if we are saying there is a wake instability, and this disturbance is the most likely disturbance, it has this Struve number, then how come the Struve number of the final flow is different? So we did a calculation. This is a DNS. Anybody can do it. So that's the drag coefficient, that's the lift coefficient, and that's the Struve number you get. So after the flow achieves the limit cycle, you get a Struve number of 0.163 as opposed to 115 predicted by the stability analysis. Okay. So we compare it. So we say, all right, let's look at the DNS and let's plot the vorticity field and subtract from this the steady state solution. Okay, that way we can only see the disturbance. So this is how the disturbance is evolving. What you will notice is that this disturbance field looks very similar to that predicted from the linear stability theory. I just showed you. Like this. The shade is a little bit darker or lighter, the structure is the same. It's very similar. But then, as time passes, it changes, the disturbance changes. That's because now the disturbance is becoming large and the nonlinear terms become important. And that's what is written here, that as nonlinear terms become important, predictions from linear stability then become less relevant. Okay, so the linear stability can only tell us something that the disturbances are small, and then when they increase, we have to again go back to nonlinear analysis. So can we get something from stability analysis of time average flows? So we can do that. So again, we decompose all the flow as a time average flow plus a perturbation and do exactly the same. This is what comes out. So if this is your time average flow now, and you must do a stability analysis of this, these are the eigenmodes that you get. Okay, and they look very similar to the disturbance of the final flow as they should. Okay, so this is what is shown here, that if you do linear stability analysis of a steady flow, that's the steady flow, these are the eigenmodes. If you do linear stability analysis of time average flow, that's the time average flow, these are the eigenmodes. But if you do a DNS, I've already shown you this column. If you calculate the disturbance with respect to steady, you get this. I've shown you already this. This looks same as these two, but then it evolves. If you do the disturbance of this flow with respect to the time average, okay, so you subtract the time average, that means this flow from all these pictures, then you get this, and the final eigenmode looks very similar to this, the linear stability analysis of the time average flow. So depending on what you want to see, you can use these tools to understand and do some analysis. Okay. So some summary before we move to the fluid structure interaction. So the linear stability of the steady flow gives useful information. The nonlinear effects are smaller. But linear stability of time average is more useful for the fully developed flow. The linear stability of the time average flow predicts the correct Struve number. But for the linear stability analysis, it does not. You can also do proper orthogonal decomposition. I not go through this, I just show you the result. If you take pictures and get the mode, you get very similar to what you get from the stability analysis of time average flow. So you get a pair of modes which have the highest energy and the modes.
And we can look at the energy content also. So most of the energy is these, and then these have smaller energy and so on. Maybe I will skip this because we are quickly running out of time. Okay. So now I want to show you linear stability analysis of a combined system and see if we can learn something from it. Okay. So all this background was just to set this up. I can already tell you that this analysis will not give us too much. Okay, all this hard work will tell us something, but not very concrete. Okay, just to remind you, there's a linear harmonic oscillator, and then the forcing is supplied by the fluid, the unsteady lift, and this is the mass ratio. We've already discussed these numbers. Okay, so when we want to combine the two sets of equations, there's a flow equation. We have already seen that. New here. And we have to be careful that we are attaching a moving frame to the cylinder, because now we are sitting on the cylinder. So, we would like to move with the cylinder. Okay. So there's a small change in the equation that we do. We add an inertial force. The structural equations I've already shown you in the previous slide. We just rewrite them in terms of ρ. So now the fluid and structure are coupled in terms of the speed at the boundary. So if my cylinder is moving with a certain speed, the fluid at the surface is also moving with the same fluid. So that's why this UV is very important. U of the body. Okay, so this is our combined equation. Now we will assume a disturbance field in terms of a steady state plus a disturbance field, and then we will expand it in an eigenmode, get equation for disturbance field, set up the eigenvalue, eigenvector problem, and solve it. So we do the linear stability analysis, U plus U prime, P plus P prime. These are the steady state equations. For structure also, if I put a steady flow, the spring will deform. Okay, so that deformation is also calculated. And then I get the equations for the disturbance field. So these are the equations. So I linearize them by dropping the non-linear terms. These are for the flow, these are for the structure. Then I put these eigenmodes. The U prime is U hat e to the lambda t, and this body also has an eigenfunction and e to the lambda t. And I solve for this whole problem together. The type of eigenvalue I get is the real part, imaginary part, and this is the eigenmode. So after doing this, if I do Reynolds number 60, these are the type of eigenmodes that I get. Okay, so let me walk you through. So the x-axis is the reduced speed, u star. And the y-axis is lambda r. Maybe we should first look at this picture. So there are two mass ratios given here. A mass ratio of 20 and a mass ratio of 5. What we find is, if I look at mass ratio 20, which is a relatively higher mass ratio, there are two modes that are they have the largest real part, candidates for instability. This one I call as WM, the wake mode. And this is the SM, the structural mode. How do I identify that? Actually from the Stuha number. So this is my F star. So notice that if I have the structural mode, that is very close to the natural frequency. Okay, so that's why it is called the structural mode. And the wake mode is, it has a frequency as if it was just a stationary system, just doing your. So it would be a constant Stuha number. But F star is a port changing. If I plot on these two axes, so I combine these two plots and I plot lambda r versus u star, then this guy forms a ring and the structural mode actually looks like this. So that's why I'm calling them decoupled. Okay, so the system has two modes. One is as if it was stationary and there was vortex shedding, and the other is now the spring is doing something and there's a natural frequency of it. So that's the blue line. That guy is becoming unstable only in a small zone there. Everywhere else it is stable. Okay. So to summarize, for the M star 20 case, the wake mode is always unstable, as it should be, because vortex shedding is going on irrespective of the spring. And the structural mode becomes unstable only in a small regime of U star. If you go to a small value of M star, okay, then something very interesting happens. These two modes, they get coupled. So look at this red line. So it initially follows the wake mode, and then it follows the structural mode. Then the blue line here initially follows this structural mode and later follows the wake mode. So this is a coupled mode. For some U star, it behaves like the wake mode. For other U star, it behaves like a structural mode. And that actually comes up very nicely in this. This is, we call it the aeroelastic mode. And this is how the eigen modes look like. So these are the decoupled modes. So this is structural mode as it evolves with U star, and this is the wake mode as it evolves with U star. And if it is coupled, it evolves like this. I don't want to bore you with more details. If you are interested, you can read the paper. I've given you some positive hints. Okay. So first question is, when are these modes coupled and when are they decoupled? Okay, so we carried out an exercise. So this is M star. This is Reynolds number, but it is also non-dimensionalized with RE0, the critical Reynolds. So Reynolds number is marked here. So here you get decoupled modes, and then so there's a critical mass ratio below which the modes are coupled and above which they get decoupled. So the writing is very clear. If you go to reasonably large Reynolds number, the modes are very clear. Okay, so either it's a wake mode or it's a structural mode. But if you go to small M star, then there will be confusion. There will be confusion between wake mode and structural mode. So first question is already answered from this picture, and let me help you with that. We have seen that if I take large M star systems, they will vibrate close to natural frequency. If I take low M star system, then we don't know what the frequency will be. And the answer is because the modes are of the mixed type, they are confused between structural modes and the wake modes. And that's why you get low frequency. Okay, so this is from so this is plotted for Reynolds number 60. This is the linear stability analysis, and this is what you get from DNS. Clearly, the lock-in region is explained. So wherever the structural mode is actually unstable, that's the lock-in regime. So that is explained. But the frequency is not explained. Frequencies are different. So what does LSA tell us and what does it not tell us? So one is, if I look at the growth rate, this is the wake mode, this is the structural mode. The maximum amplitude is here in reality, but the wake mode, the largest growth rate is here. So largest growth rate does not imply largest response amplitude. Very unfortunate. And instability does not imply lock-in. Why? I mean, this mode is always unstable. The wake mode is always unstable. But that doesn't mean there will be a lock-in everywhere. Lock-in is decided by some other modes. So we don't know which of the two modes leads to lock-in and what happens to the amplitude and what determines the final frequency. So I will just leave you with some thoughts because I've taken already too much time. So I'll quickly go through this, but but if you are interested, you can read the paper, and I'll be happy to answer your questions. We thought it would be appropriate to look at the energy transfer. So here's the physics. There's a flow past a circular cylinder. There's a base flow, okay, the steady state flow. Now it starts vibrating. So where is the energy coming from? It has to come from the base flow. The base flow has infinite energy. It's an unbounded flow, right? So if I today look at flow past an aircraft, okay, so I think of aircraft being stationary and air coming at it. What is the energy of that flow? It's infinite because the whole universe is going past the aircraft in some sense. If I have an unstable mode, it is actually picking up energy from the base flow and funding itself to become large amplitude. Okay, so I must look at energy from the flow coming into the springs. So that kind of energetics was done. We defined an energy ratio, saying that let us look at the energy of the structure, which is the mass and the disturbance field, versus the energy of the entire fluid, and we call this as the energy ratio. And then we try to look at when does nonlinearity go in, because if it's a linear flow, it will keep increasing exponentially, and at the onset of nonlinearity, it will saturate. So we did some order of magnitude analysis, and actually you are able to predict when should the system become nonlinearly active. And then we were also trying to figure out which of these things they lead to the lock-in, which of these modes, and we looked at the energy transfer. So the answer was that all eigenmodes modes with energy ratio greater than a certain threshold will lead to lock-in. But the final frequency is determined by the nonlinear process. So it's a tough question as to which causes lock-in. Structural mode causes lock-in in some part, and the wave mode causes lock-in in some other part. It's not clear at all. But you can ascribe one to each instability. It turns out the phase is very important. So I'll just close with this slide. The phase is very important. Okay. The phase between CL and Y. So these are the phase plots for 6 and 8, these are values. And what we found is that the phases are plotted here. So from the direct time integration, we get this phase, the red line, and the phase plots for the structural mode and the wave mode are also plotted here. So phase jump occurs when the phase from LSA crosses 90 degrees. This is one learning that we got, and of course, nonlinear effects are important. So to put a long story short, you can of course read this paper. The linear stability analysis provides some answer. We know a little bit more, but the bulk of the action takes place during nonlinearities, and therefore linear stability analysis is silent. And it is still not clear why fluid structure interaction has affinity for close to zero added mass. This is a question that was asked yesterday as well. So I'll stop here. I know this has been a little bit of a heavy analysis for you, but the idea was not that you understand everything, but just to give you an exposure. Thank you. I don't think there will be questions.
But coupling that we are doing at the interface, will it, go for the penetration of the effect of the body?
Can you elaborate more?
The effect, the effect of the motion of the body in the fluid, will it go, will it go for the, will it, account for?
Yes, absolutely. What you are doing is there are these governing equations for fluid, and there is a governing equation for structure. How are they coupled? To the boundary condition. Right? So if you can just
give that information back and forth. So what is the fluid doing? Fluid is applying a force on the body. And what is the body doing? Body is moving and moving the fluid with it. So if you have that in place, you're all set. It's done.
I come from civil engineering, hydraulic engineering background. So normally whenever I read the papers in the field, they limit themselves to RAN simulation and LES simulation because of the multi-phase flow, as well as like when you're simulating sediment transport. So the computational capacity that is required increases very high. But you have shown the results only for DNS simulation, direct simulation. So can you please tell me what was like the computational cost required for such simulation?
Good question. So these are very low Reynolds number. Okay, Reynolds number of 60, 100, 150 maximum. Actually, the word DNS is not a good word here. Okay, that's why I use the term DTI, direct time integration. But because people will be confused, that's why I refer to it as DNS. If you go to Reynolds number of, let's say, even 10,000 or 100,000, the cost for population is going to kill you. There is no way you can do a DNS. So LES is already a challenge, and RANS is more practical. Okay, so I don't think you can do a DNS for these systems at those Reynolds numbers. It would not be workable. LES is workable, but more practical would be RANS. So RANS will miss out on some details, but you may get a general idea. LES will pick up everything, almost everything you want. Okay? The kind of analysis that I showed you, doing a linear stability analysis, those is to understand the fundamental nature of these. Why are these things happening? But in field, you may not want to get to those questions. You are more interested in practical questions. So I think LES is absolutely fine, but that also may not be doable. So you may want to do something like DES, detached eddy simulation. Okay. So detached eddy simulation is like a hybrid of RANS and LES. So you use LES away from the wall, and you use a turbulence model close to the wall. You can read about that.
Sir? Instead of linear stability analysis, if we do DMD of this problem, because it also gives us rich value, basically that is the real part of eigenvalue. And the same thing which you told that if its value is smaller than 1, basically it's decaying, and if it's larger than 1, then is there any difference of like qualitative difference between the results which will be given by the DMD and the linear stability analysis?
Yes, there would be a difference. So all these analysis that you can do, like POD, DMD, they assume you are working on a limit cycle, and then you are using those information to analyze. What was on my mind is that when the disturbance is small, we are very nascent stages. Does the system already know where it is going? Okay, so those questions, of course, we asked those questions, and not much came out of it. So you can say that, what did you get out of it? But it's not done. I mean, somebody else may find something. So those analyses still have a place. But you are right. DMD will tell you a lot. That's the least you can do.
Because, for example, if we have different DMD modes, sir, and each DMD mode is having some type of different temporal frequency they are giving, and if you can find out which is like growing, which is outside of like the circle, then easily we can like suppress those modes. Like, I don't know how, but we can suppress those modes.
You are right. I mean, you will get some information, and people do that. They are definitely doing that. That's a very good diagnostics. But there are some questions that only linear stability analysis can answer. So I'm not saying you should not do DMD. I'm not even saying it will not give you useful information, of course it will. All I'm advocating is that linear stability analysis can also address some important questions which other methods may not be able to. So there is a case for doing stability analysis. You had a question.
So, in your opinion, what is the most robust way of differentiating between the braking stability, CLT stability, and the boundary level?
Okay. So we've done some work on airfoils where we have documented the wake instability and the shear air instability. So one would be the frequencies, the Stewart numbers. Okay, so they show very different scaling. So the way a wake instability scales with Reynolds number and the way a shear layer instability scales are quite different. The boundary layer is a little bit easier because boundary layer is, those famous instabilities where you will first get those torn restricting waves and the hairpins and then the turbulent spots. So those are easier to find out, but these two are a little bit more difficult. There's a very nice paper by Williamson and then a follow by the Monash group where they do these scalings. We've also done a little bit, but there could be situations where they have very comparable frequencies. Then the frequency may not be a good way, but we'll have to think of another way.
More question? If we can take a break, small break, and then we start the next one.
Thank you. The last session will not be so heavy, okay? We'll come back to practical problems.
Thank you, sir. Small break, and then we come back.
Or if I transfer it, double up. Can you call? Yes, yes.
What are the variations can be observed if we the reference number along with the mass?
About mass ratio or Reynolds number?
Sir, actually this question is from the last session. I have this question from the last session where in a graph you have described about the increasing order for the Reynolds number as well as for the mass ratio. And today also I have seen about mass ratio in one of the plot. So my question is that we increase both of them.
I see.
So what are the variations that can be observed for both the modes?
So one thing is if you go to higher mass ratio, as far as the frequencies are concerned, they get closer to the natural frequency. Because the added mass becomes decreasingly small. See, if I am pushing a system, water or air, then I am pushing an added mass. The amount of mass that I push compared to the mass of the system itself, that ratio will become smaller as I go to higher MC. So I will go towards natural frequencies more closely. That is one thing. The other problem is, so that's a simplification.
In that case, at one point of time, it will be diminished completely.
Yes.
Very.
Added mass will not be very important. But the problem is that you get other instabilities, like I showed you in the last class. That same Reynolds number, if you increase M star, you get different branches.
Yeah.
You get multiple states.
Yeah.
I don't know why that happens, but one has to vary on that. So there's some simplification, there's some complication. And Reynolds number is once the flow is not so organized, there's a lot of randomness. On top of that, you add another instability. So we have stayed away from high runner summer.